conversation of energy by talking about the conservation of energy. And if you remember, we have talked about work, kinetic energy, and two different kinds of potential energy, elastic and gravitational. Before we get started on the slides, I wanted to show you the homework problem so that throughout the video you can keep an eye out for how to solve a problem like this. So the Kingda Ka roller coaster at Six Flags, New Jersey is the tallest steel roller coaster with a total height of 139 meters. From here to here, 139 meters. Ignoring friction and air resistance, what is the minimum speed the cart must reach at the beginning of the incline, right here, so that it comes to a stop at the top of the track? So in order to talk about the conservation of energy, we need to talk about conservative and non-conservative forces. If friction is present, the work done on an object depends not only on the starting and ending points, but also on the path taken. And we call friction a non-conservative force. So if we look at the diagram of these boxes, if this is the starting point and this is the ending point, the amount of work done is going to be different whether you push it in a straight line or you push it in an arc. And that's because friction is present. If this were being done on a frictionless surface, it would not matter. The amount of work done on the box would be the same. But because friction is present, because a non-conservative force is present, the path matters. Potential energy can only be defined for conservative forces. So forces that on which the path does not depend. So conservative forces are gravitational forces, elastic forces, and electric forces. It turns out that for all of these, the path taken does not matter. What matters is the starting point and the ending point. However, non-conservative forces like friction, air resistance, tension, propulsion, or push or pull, the path does matter. The more work you do will happen because of a longer path. So we distinguish between the work done by conservative forces, like elastic and gravitational, and the work done by non-conservative forces, like a push or a pull from a person and friction. And we find that the work done by a non-conservative force, like friction, is equal to the total change in kinetic and potential energies. So if we take the kinetic energy of an object before and after and find the difference, we have final minus initial, and we add that to the amount of potential energy in the beginning and the end. Whatever is left here is the work done by non-conservative forces. So take the change in kinetic energy, add the change in potential energy, and that will tell you how much work a person does pushing or pulling, or how much work does from tension in a cord, like a string, or friction or air resistance. But what we're really concerned about is that if there are no non-conservative forces, if we ignore air resistance and friction, the sum of the changes in kinetic energy and in potential energy is zero, which means the kinetic and potential energy changes are equal but opposite in the sign. So however much kinetic energy you gain, you lose that much potential energy. Or, however much kinetic energy you gain, you lose that much potential energy. I may have just said the same thing twice, but I think you understand. So what that means is if we add the amount of kinetic energy in an object and the amount of potential energy in an object, that will tell us how much energy there is total in that system. And this is the principle of the conservation of mechanical energy. If there are no non-conservative forces acting on an object, the total energy in the system remains constant. And this is a really, really important point, As long as we ignore friction and air resistance and we don't have someone pushing or pulling on something, the amount of energy in that system will stay the same. The changes in one kind of energy will be the same as the changes in another kind. So here's a pretty good example. This is from Paul Hewitt, who is the conceptual physics guru. So take a look. All right, it's not working, but all right, I don't know why this is not working properly. That's a bummer. It's a really cool demonstration, but we'll just move on. So in the image to the left, there is a guy holding a boulder, and then he drops it. Up at the top where he's holding the boulder, it is not moving yet, so it doesn't have any kinetic energy. But it is raised at some distance above the ground, at some height above the ground. So we say it has gravitational potential. So the kind of energy in the boulder right here in the system is all gravitational potential. Halfway down, it is moving, but it's still some distance above the ground. So at this point, right in the middle, the total energy in that system is half kinetic and half gravitational potential. And at the bottom point, right before the rock hits the ground, it is pretty much at our zero line, what we picked as the starting point for height. So it doesn't really have any gravitational potential energy, but it's moving pretty darn fast. Gravity was pulling down on it, made it accelerate at a rate of 9.8 meters per second squared, so it's going pretty fast. So it does have kinetic energy, and all of the energy at this bottom point is kinetic. In order to figure out or calculate the total energy in the system, we have to take the amount of kinetic energy and add it to the amount of potential energy. And in this situation, there is no elastic potential energy. We're only concerned with kinetic and gravitational potential. So we want to go ahead and replace these symbols with their equations. And the equation for kinetic energy, 1/2 mv squared, and the equation for gravitational potential energy is mass times gravity times height, or y. So if we were to break this down in a visual way, we have these little things called energy buckets. You can think of them as a bucket, and when they're full to the top, that's the total amount of energy that is in that system. And if you look at the three different buckets, the amount of energy in each one does not change. It's filled to the same level every time. The only thing that does change is what it's filled with. So in the first part, in the first situation, it is all potential energy. And it's all gravitational potential energy because this rock is lifted some distance above the ground, and we're not worried about any springs or any bendy things, nothing elastic. So it's all gravitational potential energy. At the second point, halfway down, it's an even split between kinetic energy and gravitational potential energy. The total amount of energy is the same, but it's broken down a different way. And finally, at the bottom position, it's all kinetic energy. If we were looking at something with an elastic force, the conservation of energy would tell us energy is equal to kinetic energy plus potential energy. And if we weren't concerned with the height of this pole vaulter, we could say that the potential energy is elastic potential energy. So then we replace these with the equations. Kinetic energy is 1/2 mv squared, and elastic potential energy is 1/2 kx squared. And remember, K is the spring constant, and X is the displacement of the spring. So you always want to use this principle when solving problems like this. The total amount of energy when non-conservative forces are not present is kinetic energy plus potential energy. Then your job is to figure out, okay, what kind of potential energy is here? Gravitational, elastic, or maybe a little of both. Once you figure that out, you can plug in the equations, put some numbers in there, and go. When you look at a roller coaster, if there's no friction, the speed of the roller coaster will depend only on its starting point compared to its height. So if we go ahead and call this 0, because remember when we're talking about gravitational potential energy, we can call our starting point whatever we want as long as we're consistent. If we call this bottom trough a height of 0, then the speed here only depends on this distance. Why? Because the total energy in a system is kinetic energy plus potential. There is no elastic potential here, so we're going to go ahead and say gravitational potential energy. And at this point right here, right before it starts moving down the hill, it's all gravitational potential energy. If we look down at the bottom, we call this our 0 mark. It is 0 height, 0 meters above our starting point. So there is no gravitational potential. So it must be all kinetic energy at this point, the energy in this system. And then at this point, it's some mix. It has kinetic energy as it's moving up the hill and gravitational potential as it's being raised above our 0 mark. So let's do an example. Nolan Ryan reportedly had the fastest pitch in baseball, clocked at 100.9 miles an hour, or 45 meters per second. This is incredibly fast. If such a pitch had been directed vertically upwards at the same speed, then to what height would it have traveled? So the very first thing that I'm going to do is draw a picture. Huge fan of drawing pictures. So we have Nolan Ryan down here. He has a baseball cap on. And he is throwing a baseball upward, as fast as he can. So if the ball travels up, if we go ahead and say the point at which the ball leaves his hand is a height of 0, what kind of energy must the ball have at this point? Well, if it's at the 0 height, it doesn't have any gravitational potential. There might be some elastic potential here in his muscles, but we're going to go ahead and say that it's pretty close to 0. So the only kind of energy at this point is kinetic. The ball is moving, all of the energy within that system is kinetic energy. At the very top, the ball stops at the top of an arc, right? It has to stop going up in order to start coming back down with gravity pulling on it. So it doesn't have any kinetic energy. There is no elastic potential energy. So it has to be all gravitational. So what that tells us is energy, total energy in a system, as long as we're ignoring air resistance, is kinetic energy plus potential energy. So we can go ahead and put our equations in here now. Kinetic energy is 1/2 mv squared. Potential energy, it's gravitational here, so it's mgh. And what I've done here is I've said that the total energy before, when he is throwing the ball up right as it leaves his hand, is equal to the total energy after. Because we know since air resistance is not acting on this thing, there will be no energy loss. The amount of energy when the ball leaves his hand will be the same as the amount when it gets to the top of the arc. The only difference will be what kind of energy it's made up of. So now we can go ahead and start plugging in some numbers. So we have 1/2 mass velocity for the first bit is 45. Gravity is always 9.8 meters per second squared. And at the very bottom part, at the first position, we called that height 0. So we can go ahead and put a 0 in there. For the second part, where the ball is at the top of the arc, we have 1/2 m. And the ball stops at the top of the arc. It's not going up anymore, but it hasn't started falling back down yet. So it has a velocity of 0. And then gravitational potential, remember, gravity is always 9.8, but we don't know how high it's going. That's what we're trying to figure out. And you may be looking at this and you may be a little confused because you think, okay, we have h in there as an unknown, which is good. That's what we're trying to solve for. But we also have a bunch of m's. How are we going to solve this problem if we have a bunch of m's laying around? Well, if you look closely, there is an m in each part. There's one here, one here, one here, one here. In each part, separated by our addition signs and the equal sign, there is an m. And what that means is if there is an m present in every single part that's separated by some function and an equal sign, means you can get rid of it. It's going to cancel itself out. So what we can do is go ahead and cross out all of the m's. And that's going to make our life a lot easier. So now we rewrite it to simplify, and we have 1/2 45 squared. This whole thing goes to 0 because we have 9.8 times 0. The whole kinetic energy bit on the second position goes to 0 plus 9.8 times h. And that makes sense, right? We determined that at this beginning position, the energy was all kinetic. There was no potential. And that is reflected here. In the second position, we said it's all gravitational potential and no kinetic, and that's also reflected here. So now, if we plug 1/2 of 45 squared into our calculator, we do 45 squared times 1/2, we get 1012.5 equals 9.8 times h. And to get the height, we have to divide both sides by 9.8. So it turns out this baseball would travel about 103 meters. That's pretty incredible. So all of that kinetic energy stored up in that baseball, because of the incredibly high velocity, would translate into a pretty big amount of gravitational potential. And that's reflected in the really, really high distance that this ball would travel. So when you're doing problems like this, I would go ahead and follow the same steps. Draw a picture, identify the types of energies at each position, figure out what kinds of energies are involved, substitute in the equation for each type, and then plug in your numbers. So go ahead and use this as a reference for your homework problem. If you follow the steps, you should be in pretty good shape to finishing this problem.